Okay, let's get started. So, good afternoon. How are you doing? Was the weekend busy? So. So today we'll continue the logical database design. So today I'd like to explain about the normalization and then normal forms, first, second, third, and BCNF, and fourth, if possible. Then some kind of the terminology. Okay, we'll continue about this. Do you have any questions about project or anything else? No? Okay. Okay, so keys. Key, you know that, the key. What is the key? The key is the column to identify all other the columns. So it should be unique in a relation or table, right? So the key can be a single or the composite. So combination of one or more columns to identify the rows in a relation. And the composite key means consists of two or more the columns. So you know that. And then what is the determinant? You remember determinant? Determinant is, okay, when you have those kind of relationship, cookie cost calculated by number of box times $5 per box. In that case, the cookie cost determined by number of box. So in the left side, left term, number of box is called determinant. So in a relation like the stock, keeping unit data, SKU description, department, buyer, that column determines all other columns. And then description also determine SKU, department, and the buyer. And another one, the buyer determinant department. So in the left side, left term is called determinant. So there are three determinants: buyer description, and SKU description, and then buyer. So those are called determinant. And then candidate key is the determinant that determines all other columns in a relation. In a previous example, SKU description determine all other columns. Those are determine all other columns. But the buyer only determines what? Department. Partially the determinant, not all of them. So in that case, the buyer cannot be a candidate key. Only there are two candidate key, SKU description. Okay. Then the primary key is we choose. So one of the candidate key to use as the unique column. Okay. So this is a relationship and then definition of a terminology. So related to the primary key, there is the constraint. It is called entity integrate constraint. So when you create table like that. Create table, test table, ID, name, telephone. There are 3 columns. So if we want to use ID as a primary key, we add 1 keyword, not no. What does that mean, not no? Mm-hmm. Mm-hmm. Yeah, that's right. So if you select primary key, the primary key always has the value, the unique value. It is called entity integrity constraint. So, the SQL workbench, we use command not no. If not, the, the DBMS, the raise the error. You have to specify not no to primary key. Okay? So this entity integrity constraint is related to the primary key. And the other surrogate key. So what is the surrogate key? The definition is artificial column added to a relation to serve as a primary key. So that key should be supported by the DBMS. But usually the commercial DBMS, the support their surrogate key. And then short and numeric, and then never change. And the artificial value means the meaningless to users. Just identify the, the laws. So what does that surrogate? Think about if we want to create a rental property relation. So in this relation, we can add several columns. For example, street, city, state or province, zip or postal code, country, rental rate, and so on. So think about those columns. So you have to select primary key. So which column will be the primary key? You can choose. Yeah, so the column cannot be used as a primary key. Why? Street. Street, a lot of property, house, apartment, city, state. You cannot. So we have to create composite key with 1, 2, 3, 4 columns. So you can do that, but what's the disadvantage about the composite key with the 4 columns? Mm-hmm. Mm-hmm. That's right. That's right. So, and also if you want to join with other relation, you have to create the long statement. Like rental property dot street is equal to other relation dot street, and rental property dot city should be equal to other relation dot city. Add all conditions. It should be long. That means you're the SQL statement error prone. Okay, so to avoid this kind of situation, we add artificial number. In this case, property ID. For example, 20, 25, ABC, 1, 2, 3, something like that. Okay. So if we use this property ID as a primary key, we don't have to create composite key, street, city, state, zip code. So this property ID the column can be used as a primary key. So this artificial number, right, column is called the surrogate key. Okay. And so take a look at the example. This is a relation, the table. So buyer, there are 4 columns: buyer name, department, position, supervisor, and there are 5 rows. So buyer name, department, position, and then we select buyer name as a primary key. Maybe possible, right? But take a look at the value in a primary key. So for example, Mary Smith. In this, usually there are 2 words, 2 parts: Mary Smith first name and then last name, right? So you may split into first name and last name. And another situation, we have just 5 rows, but the Mary Smith is just unique. It's unique. But if you have 1 million rows, but Mary Smith is a common name, so there are multiple Mary Smiths. In that case, we cannot use buyer name as a primary key. So in short, we create add the surrogate key like a buyer ID or any kind of ID, the numeric number or the alphabet. And then we split first name and last name, create 2 columns like that. So if those kind of table, the relation is given to you, you have to think, how can I create the relation to insert database? So not exactly, you can create the table as it is, but think more and then try to think efficient way how to uh, create the relation better way. Like if need, we can add surrogate key, and then we split columns into 2 or 3, depends on the situations. After that, we can create the table relation to the DBMS. This is the approach. Then next is a foreign key. So foreign key definition is column or composite of columns that is the primary key of table other than the one in appears. So which means if you have 2 tables, so the foreign key can be used to connect or reference or combine or tie together. Then there are several ways to represent foreign key. So in this PowerPoint, this material, so foreign key is written by italic, and underline means the primary key. So we have the 2 relation, department employee, underlined means department name is primary key, and then employee relation table, employee number is primary key, department is italic. That means foreign key. So 2 relations tables are tied together. Is the foreign key department is mapping to the department name in the department relation. Okay, and So related to the foreign key, there's another the constraint, referential integrity constraint. What does that mean? So that is, statement limit the value of the foreign key to those already existing as a primary key value in corresponding relation. So it can be represented like that. What does that mean? The SKU is a column, it's a primary key, not a primary key here. SKU data and SKU is a primary key. That one. Like this. So this is a foreign key order item. This is a foreign key. And then the values here should be existed in the primary key in the SKU data. For example, like 101, 200. So 101, 200. It should be exist there. Maybe if you create 400, 100. But it should be existed there. But if not, it violates the referential integrity constraint. So the values of the foreign key, these values should be existed in the primary key. Okay, so that is the referential integrity constraint. So domain integrity constraint, what is this? Entity integrity constraints and the referential integrity constraints as a whole is called data integrity. Okay. Yeah. So domain, entity, and then referential. Do you remember domain integrity constraint? Yeah, yeah. It's a nice try. Yeah, nice try. 219, page 19. If you read this one, you can recall easily. Okay. So same kind of the data. First name should be first name in all other rows. Last name, all rows should have the last name. That is the domain integrity constraint. Okay. Yeah. Uh-huh. Okay, the main. So normal forms. So I think in logical database design, the normalization, the process to make normal form is normalization. So this concept is the most important concept, okay, to design the database, the relational table, okay? So what is that? So there are some kind of the assumption, and then the status of the table. So all tables, all relations are not equal. What do you think? Maybe. Okay. Some are easy to process and others are problematic. Or some relation has a couple of columns, but some relation has a lot of columns. And then some relation has several rows, the data. But some relations has a lot of rows, 1 million, 2 million. Okay, so we don't know. It depends on the data of the business or company. Okay, then so the relations, the tables are categorized into normal forms: first, second, third, BCNF, fourth, fifth, and so on. There are the high order of normal form, but I'd like to introduce fourth normal forms. Okay, so again, relations are categorized into normal forms based on what problem they have. If you have a relation, if the relation is not perfect, they have some potential problem. So according to the potential problem, we can define this relation in first normal form, this relation in second, or third, or fourth, the normal form. Okay. Then, so knowledge of this normal form will help you create appropriate database design. Okay. Yeah, before that, so what kind of problems? Here in the definition, so relation can have the problem. So what kind of problem? It is called the anomaly, the modification anomaly. So there are three anomalies: deletion, insertion, update. Okay. Take a look at the first, deletion anomaly. In this table, how many columns? 1, 2, 3, the 6 columns. Item number, equipment type, some cost, repair number, repair date, repair cost. So those 3 columns are related to the machine, and the other 3 columns are related to the repair. Just combine. So here, maybe, okay, take a look at the second row, this one. This is unique. The repair number is 2100. So this is an example of a deletion. If you delete repair number 2100, so in order to delete this data, also 200, late 4750, these data also should be deleted, right? Because they are in the one row. So if you delete this one, this second row, what happened? Lose everything. But take a look at this. Machine equipment type rate is only once. But if you delete this row, that equipment is disappeared. We don't know, right? But the others it's okay. So drill press 1, 2, 3, 4. If you delete one of them, but still drill press, the data existed. It is the same, but it's a deletion anomaly. If you delete the row, the entire data about late or meal also gone. So deletion, the anomaly. And then maybe this example is more better. I think it's better. So here, this is a customer and the salesperson. So if the Western hardware left, so terminate the business, the general hardware. So I'd like to remove Western hardware from the database. If you delete, the salesperson also gone, also disappeared. But in this case, the Dickens is only one. So salesperson data also deleted. It caused a problem. But still, there's a Dickens, but in a database, no data about the Dickens. Okay, this is a deletion anomaly. And the insertion anomaly. Look this one. So new salesperson is higher, third, and then salesman number is assigned. So commission percentage 12, then year of hire 2025. So I'd like to insert third into the database table, but we cannot. Why? In order to insert third, we need additional value about his customer. If not, we cannot add third into the table. So we have to wait. The third new customer should be assigned to the third. After that, we are able to add to the table in this row. Okay. So a little bit weird. So it is called insertion anomaly. Okay. And then the update anomaly. So there are real, maybe this is more easy. So commission percentage, Baker's commission percentage is 10, Baker, yeah, here, Baker 10, Baker 10, Baker 10, then Baker 10. So 4 times. So this year, the commission percentage of Baker is updated. It's increased maybe 20%. So we have to update how many times? 1, 2, 3, and 4 times. But in this case, there's no problem. But assume that maybe 1,000 acres to commission the percentage. We have to update 1,000. Maybe if we miss once or twice, so 989 or 999. In that case, because the problem depends on which law is referred, sometimes 10, sometimes 20. So there are mismatch. So this is an update anomaly. It's a kind of potential problem. If the everything goes well, we don't have to worry about this anomaly, insertion, deletion, update. But uh, this anomaly can be happen. So potentially. So we have to try to avoid this kind of situation using normalization. Okay. So this is a summary of normalization. Source of anomaly, source of problem. What is that? Functional dependency. What is the functional dependency? Do you remember? Functional dependency. See. What is that? Functional dependency. When a value of one or the one set of attribute determines the value of a second or second set of attribute. So cookie cost, number of boxes determine cookie cost. In other words, cookie cost is functionally dependent on what? Number of boxes. So those kind of relation is functional dependency. Make sense? So from this relationship, we are able to select, determine, and determinant. Then from the determinant, we are able to get candidate key. From the candidate key, we are able to get primary key. Make sense? Okay. Here. So first, second, third, BCNF normal forms are due to functional dependency. This is a source of a problem, source of anomaly. And then fourth, the normal form is from what? Multi-valued dependency. Okay, so those data constraints and auditability, we may skip this part. Only we are focused on those five, the normal forms. Okay, so 1, 2, 3, BCNF from functional dependency, fourth from multi-valued dependency. Okay, keep in mind those, the source and then related normal forms. Okay, if so, what is the first normal form? To the previous slide. So relational database is introduced by whom? You remember? Uh-huh. Yeah, in 1970. Yeah, this guy, the code IBM engineer. So he published a paper in 1970. So according to his paper, is it? Is it? So in his paper, he defined rows of relations must be unique. So if you have the table like that, and the rows, they are unique, not the same. And then in his relation or table, there is no mention about the primary key. Okay? So in his table, there's no primary key. It can be possible why, though each row is unique. Okay, so this is his relation definition, but more improved, and then we are able to, okay, here. Okay. So require the primary key, important condition, unique. Okay, those parts cause the definition about relation. But we, the software engineer and database analyst, define the first normal form, so satisfy two conditions. One is that meet the set of conditions for relation. What is that? This is a condition for relation. Remember, there are 8 conditions. Like rows contain data about entity, columns contain data about attributes. All entries in a columns are same kind. Each column, blah, 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 blah. No 2 rows may be identical, blah, blah. So if you have a table and the table satisfy the 8 conditions, it is called relation. Okay, this is a one condition to be a first normal form. And the other form is if a relation has a primary key, it is called that relation in first normal form. Okay. So far, it's not difficult, right? Just satisfy, check the condition. So this is a set of this relation satisfy set of condition for relation, and if this relation has a primary key. If yes, the relation in first normal form. Okay. And then next, second normal form, a little bit complicated, but not too difficult. So the relation is second normal form when first condition is the relation should be in first normal form, satisfy the previous normal form, and then all non-key attributes are determined by the entire primary key. Okay, so take a look at the example. If we have a relation, the relation called R, capital R. There are how many columns? 5 columns, A, B, N, O, P. And then, so primary key is a composite primary key, consists of A and B. So then here, none of the non-key attribute N, O, or P can be determined by just A or B. For a specific example, student activity, this is a relation. How many columns? Student ID, activity, activity fee. So student ID and activity is a composite primary key. So this composite primary key determine what? Non-key attribute, activity fee. If we know the activity, we are able to calculate the fee. Okay, so this relationship makes sense. And then take a look at activity and then activity fee. If you know the activity, we are able to calculate fee without student ID. Activity determines activity fee, right? So what is the definition of the second normal form? All non-key attributes are determined by the entire primary key. But in this case, the primary key activity determines non-key attribute activity fee. So it violates this condition. Make sense? No? Again? So student activity relation. There are 3: student ID and activity. and then activity, the fee. So in a relation, we set composite primary key, student ID, and activity. Okay, this is assumption. The primary key is student ID and then activity. So that primary key determines what? Non-key attribute, the activity, the fee. Make sense? And then to be in the second normal form, this condition should be satisfied. What is that? Entire primary key determine non-key attribute. Entire composite primary key determine non-key attribute. But when you take a look at activity and activity fee, so activity determines activity fee also. It's a part, it's partial of the composite primary key. So it violates the second condition. All non-key attributes are determined by entire primary key. So in this case, this is the first normal form, but not second normal form. Make sense? So we have to split the relation into multiple relation. How? This is what do we have to do? So move the columns of a functional dependency based on partial primary attribute. Which one? Activity. Determine activity P. This is a partial dependency relationship. So those two columns move to the new relation, like create another relation called activity fee, and then move activity and activity fee into the new table. And then leave the determinant in the original relation as a foreign key. See, this is the original key, and that one is a determinant so for activity fee. So this activity used as a foreign key, like that. So that relation is split into two relations. Student activity with two column and the new activity fee column, activity relation with two columns. So this activity is a foreign key to tie activity fee relation. Yeah, primary key in a new table, but the activity is a foreign key in the original relation. Make sense? Okay. This is so in this case, student activity and then activity fee are in the second normal form. Okay, it's the second. How about the third? Relation is in third normal form when satisfy two conditions. One is that relation should be second normal form and satisfying no non-key attributes determined by another non-key attribute. Okay. Think about that, this example. Relation R, there are 5 columns, A, B, N, O, P, and then A, B are composite primary key. So none of the non-key attribute NOP can be determined by NOP. So student housing is a relation. We have the three column, student ID, the building, and then building fee. So the building, so this is this relation in second normal form. Why? But so two, we have to think this is a second normal form if the primary key is composite key. We have to think to be a second normal form or not. But in this case, only one single the primary key, so we don't have to think a second normal form. It cannot split into two parts. We have only single the primary the column, right? So absolutely, this is a second normal form. Okay. So student ID, determine buildings, and then building P, right? And how about building and then building fee? There is some relationship. What kind of relationship? If you know which building, we know the fee. So building, if we know the building, we know the building, the fee. What is the building? It is not a primary key. It's a uh, non, non-key column attribute. How about the building fee? It also non-key attribute. There is a relationship between non-key attributes. So that relationship violates one of the conditions. Non-key attribute cannot determine the other non-key attribute. Make sense? No. Again, so to be in third normal form, the relation should be in second normal form, and then uh, none of the non-key attributes can be determined by none of the non-key attributes. But in this example, building is non-key attribute. Building P is non-key attribute. But the building determines building P. So it violates this condition. So this relation is not in second normal form. So how we have to modify the relation? So this is explanation. Okay. So first of all, we move the columns of the functional dependency. So building and then building fee. Building and then building fee. Between non-key attributes. There is a new relation. And then the original relation, student housing. So we just leave student ID and then building used as a foreign key.
So that's essentially what we did.
Mm-hmm. Mm-hmm. Yeah. Second normal form is related to the composite primary key. And then we have to check the part of the composite primary key attribute, non-key attributes, but that is the second normal form. But third normal form, non-key attribute determine other non-key attribute, in that case, it's related to the third normal form. Make sense? So we split into two relations. Okay. This is a third normal form. Make sense? And the other one, BCNF, is a voice code normal form. So a little bit. Okay. So a relation is in BCNF if and only if it is third normal form. Okay. To be a second normal form, it should be first normal form. To be a third normal form, it should be a second normal form. Okay. Like that. And then another condition. Every determinant is a candidate key to be a BCNF, voice code normal form. So consider this relation. Student advisor. There are three columns: student ID, major, advisor name. So try to think what kind of relationships, functional dependency exist. Student ID can determine major. What do you think? Student ID determine the major? Maybe not. Why? 300 and 800 associated with psychology and math associated with the two multiple the value. So no functional dependency. How about maybe student ID can determine advisor name? Maybe not. 700 associate course. Another 700 is associate Riemann. So multiple means student ID cannot determine advisor name. Make sense? Okay. So here, student ID does not determine major, and student ID does not determine advisor name. So to set primary key or the candidate key, we have to create composite key. Think about that. Student ID and then major. Student ID and then major. Determine non-key attribute, advisor name. What do you think? Student ID and major can determine advisor name. Yes, because 700 psychology associates with the Pearl. 700 math associate Riemann. So associates are different the value. 800 math Cauchy, 800 psychology Zhang. So different value. So you can say that student ID major determines advisor name. Okay, so from this relationship, we can have student ID and the major determines advisor name. And another one, think about that. Student and advisor name can determine major. Yes. 700 course is associated with psychology. 700 Riemann associated with a different value. So you can say that student ID, advisor name, determine major. So we obtained another relationship. Student advisor, student ID, and advisor name, the composite primary key. And then in this case, major is what? Non-key attribute. So those are these student advisor in second normal form and then third normal form, right? What do you think? Is a second normal form? Second normal form, part of the composite primary key cannot determine non-key attributes. So part of the composite primary key, student ID can determine advisor name? No, we say student ID cannot determine major. So this not satisfied. And the major determine advisor name, major math, determine Riemann and Cauchy, associated multiple. So major part of the composite primary key cannot determine advisor name. So only student ID and the major can determine non-key attribute. So you satisfy the partial dependency. No? Used. Okay. So to be in second normal form, okay, here, none of the non-key attributes can be determined by A or B. Only entire composite primary key should determine non-key attribute. So entire composite primary key, student ID and major can determine advisor name. Student ID, advisor cannot determine advisor name. Major cannot determine advisor name. Make sense? Confused? Yeah, so that's what I'm talking about, the PCNF condition. Okay, so, and then this is second, normal form, and third. So we have only a single non-attribute. So absolutely, obviously, it satisfies the third normal form. Third normal form should be is related to non-key attribute, right? But in this relation, we have only one non-key attribute. So obviously satisfy the condition of third normal form. But think about like, but in this relation, two relationship, so two here, maybe so student ID and the major, or student ID and advisor name, there are two determinant. In other words, two candidate key. Okay, so it is called overlapping candidate keys. In here, student ID is overlapped in two candidate key. Make sense? Student ID is used twice. One is this and one is this. This overlapping candidate key. Okay. And then, so like Nico said, think about that. Advisor name and then measure the relationship. Advisor name can determine measure. What do you think? Yes, right. So like the Riemann determine associate the math, Cauchy math, Cauchy math, Cauchy math. So here, advisor name determines the measure. Okay, but important thing, advisor name can determine student ID? No, only advisor name determines what? The major. So, but not determine student ID. So advisor name cannot be a candidate, just determinant. Okay, so there are three determinant: student ID, major, this is one. Student ID, advisor name, this is two. And the last determinant, advisor name. Advisor name is only determines the major, but not candidate. But to be a BCNF, every determinant should be a candidate. This relation satisfy? No. The advisor is a determinant, not candidate. Make sense? So we have to split into two relations. So student ID, here, this determinant relationship, advisor name and the major, with those two columns, we create new relation, advisor, major, with advisor name and the major. In the original relation, we just remained the determinant advisor name as a foreign key. So primary key in a new relation, and then advisor name is a foreign key. And this one is tied with the new relation. Okay, so those student advisor, advisor majors are in BCNF. Make sense? Okay. So this is a process for bringing a relation into BCNF. Okay. So this is kind of the repeat. First, we have to find functional dependency, right, between attributes, and then find candidate key, right? So if there are functional dependency, there's a determinant which is not a candidate key, like advisor name determines major, move the columns of functional dependency into a new relation, like this one. Then make the determinant of that functional dependency primary key of a new relation, leave a copy foreign key in original relation. So this is a determinant remains in the original relation and set as a foreign key. Okay, so repeat this. It's a procedure to make the BCNF the form in a relation. Okay. This is another example. So SKU data SKU and description, department, and buyer. We know that there are three relationships and then three determinants. SKU, description, and then buyer. SKU is candidate key? Yes or no? Yes. How about the description is a candidate key? Yes. How about the buyer? No. Buyer is not candidate key, but determinant. So this table is not in BCNF. So what should do? What we have to do? Split this relation into two relation. How? Buyer department, those are maybe in short procedure. This is a like this. Create a new relation with buyer and the department. Okay, okay, this one. Okay, like that. And then it's a department from the original. Here is moved to the new table, and then buyer is remains and as a foreign key to connect the new relation. So have in the original relation is modified SKU, subscription, and then buyer. The new buyer table, buyer two, the buyer and department. So foreign key, and then this is a primary key. So that table, that relation looks like so the perfect, but in point of the normalization, there are some potential problem anomaly. So we should modify it like that. Split into the two table. So each table are SKU data 2 and the buyer 2 are in the BCNF. You know how to make normalization. First, second, third, and the BCNF. The goal of the normalization is to what? Yeah, so what is the ultimate goal or the purpose of normalization? Is remove problem the relation has. In other words, to remove potential anomaly, insertion anomaly, deletion anomaly, and update anomaly. That is a goal, to remove. So sometimes there are no anomaly, but we don't know if you update or insert and then delete the row of each table, something happened to delete the whole the data of the entity or duplicate, insert it. If we want to add just one row, but in a relation, we have to add 2 rows and 3 rows or the multiple row. Okay, so the goal of the normalization is to remove the anomalies, the problem. And the goal is to remove redundancy. Okay. So this is a result. That table relation SKU data is split into two parts like that. And then you create those tables into your database. Okay. So 5 minutes, we'll continue next week. So think about this relation and then think about what kind of relationship. So which column should be a primary key? Wow. Which columns should be a primary key? And what kind of functional dependencies exist? Mhm. 3 columns. Okay. And other relationship. Can you tell me more relationship? You should not be find. You don't have to find the primary key. Just try to find determinant first. Find the determinant, and then find the candidate from the determinant, and then find the primary key from the candidate. So start from the determinant. So what is the determinant? Which columns are determinant? Maybe complicated. In the data, actual table, more complicated than one. This is a very, very simple one. Mm-hmm. Mm-hmm. You got it. Activity determines. Where is it? Yeah. Determine activity fee. Yeah. 1. How about student ID and student name? No. Why? 100 associated with the Jones. Then 400 is also associated with what? Jones. Associated multiple values. So student ID cannot determine student name, right? Here. Let me see. Student ID. Sorry. Yeah, sorry. So student ID here 100 associate is Jones, and then 400 is associated Jones. Okay. So student ID determines the student name. Okay. So about maybe I have much the explanation I'd like to introduce about this table. Okay, so we'll continue this one the next week. Okay. So until today, what we have learned is first, second, third, and the BCNF. So please keep in mind those forms, and then how to find normalization, normal forms, and then how to split the original relation into multiple relation, satisfying first, second, third BCNF. Okay. So next week, I'd like to introduce this student activity normalization example, and then the force normalization, the process. Make sense? Any questions? Nothing? Okay. Thank you. And then have a great evening. See you next week.